So my name is Pedro Gonçalves, and I'm going to be conducting a seminar in nuclear energy. First, we're going to go through what I'm going to talk about in the presentation. I'm going to start talking about what is nuclear energy and how does it work, basically, so that we can now understand and talk about it, so that we're on the same page. The next is the question that most people ask when it comes down to nuclear energy. That is it safe? Like, can we be secure while using it? That's like something that people don't really understand quite. So I'm bringing that up. The next is like the next step when those other questions are answered is it really better? So, okay, we understand how it works. We understand that it may be safe. So is it better? We're going to answer that. And then we're going to see examples of how it is used in the world and basically, um, yeah, how it is used and the state of the art per se. And after that, we're going to see a look into the future and basically what we're going to do with nuclear energy in a few years or maybe a century. So, starting at the first point, what is nuclear energy and how does it work? In a nuclear reactor, atoms of uranium, not necessarily uranium, there are some other atoms like cesium or polonium, for example, that have radioactive properties, but mostly it's used uranium due to its abundance and facility to use, basically. So the atoms of uranium are forced to break apart, and that process is called fission. There is also another nuclear reaction that is called fusion, but we cannot use that for energy yet. So I'm going to discuss it a bit later. Uh, so basically, when the atoms break, they release particles and energy, heat at the same time, because the particles vibrate. So we release mass and energy at the same time. And that we use to heat water, basically. We have like the core of uranium, and there goes the chain reaction that like one atom breaks, then the other breaks because it hits the atom, and like the sheer force of the atomic particle breaks the atom apart, and that keeps going. Like one breaks, the other breaks and keep breaking. So that's what happens and causes a chain reaction that releases mass and heat, that is energy. And we use that very simply, actually. It's honestly kind of funny when you think about it, because we do all that just to heat water. And then we heat water, use the vapor of water to turn a turbine. And from that, we use a normal generator. So that's how we produce energy from nuclear energy. How is the nuclear fuel made? Because we don't just take uranium out of the mines and put it in the machine, the nuclear reactor. We have to process it. We have to mine it, then have to go through a process of oxidation so that the uranium becomes solid and a little less volatile, but not really. It's still very reactive, but it's more controllable because we are humans and it's way easier to manipulate a solid than a liquid. So that's why we do it. And it helps in some properties of the atom. And maybe it could help, not in all the cases, but it could help in producing the isotopes that we want to generate the chain reaction. So after that comes the main part, that is the enrichment of the uranium, that basically it's concentrating a type of uranium in basically a mixture of very large quantities of isotopes of uranium. If you don't know what an isotope is, it's basically the same type of atom, just with a different mass. Like it's still uranium, it has the same amount of protons, the same amount of electrons. The only difference is that it has different amount of neutrons. So We want a specific amount of neutrons to cause a little instability in the atom so that when it gets hit by a neutron, it shatters easily. So that's what we do when it comes down to enrichment. We concentrate and type of isotope that has less neutrons, and consequently it has less structural force, so that when we hit it with a neutron, we can break it easily. But really, it's not that much. The most part, like 98%, it's still the basic uranium, that is the 238 mass uranium. But we concentrate 2% of the 235 uranium, so that we can have the better chain reactions. So here, basically, it's how the fission works and fusion. Also, I'm going to go through a bit of that later. So nuclear fission, we heat the uranium 235, that's what I'm talking about, because it's easier to break, with a neutron, literally hit it with like shooting a bullet, the atom, and it gets more mass, but it breaks apart, like it gets a little unstable. So then it divides into this element that I don't know the name, but I think it's barium or something like that, and kryptonite, the Superman kryptonite, and three neutrons that just shoot out of the atom, and that's what causes the chain reaction. So one atom that breaks hits another three atoms that break. Normally, not all of those hit, so it's kind of a statistical thing. Like it has a chance to hit, but it's almost impossible that it hits nothing. So basically, all of three hit, and that continues to happen like in a lot of atoms. And as we do that, we release mass and energy because the particles vibrate a lot because they get heat and they start to shake basically. And nuclear fusion is a little more complicated, but it's kind of the inverted principle. We get two. This is the easiest way. There theoretically uh, are infinite ways to do it, but we cannot. So this is how we know how to do it, and this is how the sun does it. That is hydrogen deuterium, that is a type of isotope of a hydrogen, combined with another isotope of hydrogen, that is tritium. They literally collide and fuse together. They get stable, but not really. Like some parts of it get stable, but there's a little too much mass, and that's what releases the neutron, and then it combines into helium. So it gets stable as helium, but there's too much mass, and it just shoot out. And it happens the same thing. It shoots, hits another, and continues the process. Here's how a nuclear reactor works. That's what I was explaining earlier. So we have the one loop, the two loop, and the three loop cycles. They all do the same thing, but delayed. So like for one cycle, we literally boil the water, it turns into steam, turns the turbine, and that generates electricity, and then it condenses in a condenser, sorry, and that becomes water again, and the cycle repeats itself. In a two-loop cycle, we have the same thing, but it's for safety measures. Because when water boils with uranium in it, you can kind of imagine what would happen if that like spilled or shoot in a like undesirable way. So that is for safety reason. Because when we do that, we have pressurized a pressurized environment there. It's this case here. Don't know if you guys can see it, but I hope so. And it maintains pressure so that the water does not boil while heating up. And then water heats up more water, but in another pipe so that that water doesn't boil up, and it continues. And that's basically it, the whole process. Now the next big question, is it safe? Is nuclear energy really safe? Well, according to Bill Gates, nuclear energy in terms of an overall safety record is better than other energy. The key for the safety in nuclear energy is the multiple independent layers of protection and security. Like every system of a nuclear power plant is completely unrelated and undependent and onto another system. Like if something breaks, the other continues working. There's no problem. And there's a lot of layers and a lot of like reserves. Like when something breaks, there's something that does the same thing that takes its place. So it's very hard for it to break. There's also multiple physical barriers that protect against uranium spills and like radiation. So pretty safe. It's almost impossible that radiation could go through. Statistically speaking, it is possible, but not really. Everything is possible, but statistically speaking, it's not. So there are several redundant and diverse safety systems that ensure the security in the power plant. Also, the biggest problem is not usually computers or machines, it's mostly humans. So when it comes down to that, we do a lot of things that makes no need for a human to work so that we minimize human error. So we like, um, if you want to work in a power place, a power plant, you must have like 2 years of a course and extensive training. You need to tirelessly, weekly even, do simulation work in the reactor, like 5 hours plus per day. And you must be physically fit, like you need to be strong and in shape in case of danger. And also you need to be okay with your psychological self. So you cannot have psychology issues. And also, this is very important. In the modernity, we have a lot of internet attacks and DDoSs. So they also invest highly into cybersecurity. It's very hard to break into a power plant. And that's basically it. Like they are built to withstand extreme weather like hurricanes, tornadoes, earthquakes, volcano eruptions, what else? Tsunamis. Really, it's impressive. It's an impressive building. The rest is basically the same. The only things like when it comes down to throwing out the basically the trash, the uranium trash, the nuclear trash, and because we think there's a lot of it and it pollutes a lot, but not really. It really just all over the years, like from 1950 till today, it has only produced like a football field of nuclear waste. So that's pretty low when you think about it. So well, we've discussed how it works. We've seen that it's relatively safe, pretty safe. And is it better than other sources of energy? That's the now question. And well, yes and no, really. It kind of when it comes down to energy types, it's really the tool for the job, but it has a lot of advantages. For example, unlike other sources, nuclear power does not release carbon in the environment, so that's pretty good. It is a green source, and unlike hydroelectrics, for example, that we have a lot in Brazil, it does not damage the environment in its building. Like hydroelectrics, they need a lot of space and they sink a big part of the nature and the forest, and that is pretty damaging. So nuclear energy does not need that. It's kind of like a building, really, and they also work 24/7, like all day, every day. They just stop for maintenance. And that doesn't happen in other sources, like solar energy. They don't work pretty well at night. Eolic energy, they don't work when there's no wind. Hydraulic energy, hydroelectric energy. If there's no rain, we have a big problem because as we see right now, like it does not produce enough energy. So that's some of the advantages that nuclear energy has, but the main disadvantage is really the safety. But as we saw, like not really, right? It's just like a mass hysteria of the public. Like people are afraid what could happen. Because like we've seen what happened in Chernobyl, Nagasaki, Hiroshima, like not necessarily a power plant exploding, but like the nuclear bomb itself is also contributing to the fear in the technology. And like this is a very nice statistic. One uranium fuel pellet creates as much energy as a ton of coal, 149 gallons of oil, and 17,000 cubic feet of natural gas. Like this is a lot. And they usually work for 5 years before you have to change them. So that's also pretty good. So how it is used now in the world? As of 2011, about 15% of the world's electricity is generated by nuclear power plants. And wow, that's a lot, right? Nations such as Lithuania, France, and Slovakia create almost all their electricity. Like France, for example, only source of electricity is nuclear power plants and coal, and they turn off the thermoelectric power plants. Also, the USA has 92 nuclear reactors, and that's 20% of their electricity. And all major countries are basically pursuing how to dispose of the nuclear waste. That's the biggest problem when it comes down to the nuclear energy. And that's basically it for the world. But let's see a little. Oh no, actually, a little data. This is a more actualized one. So according to May 2019, and data from the WNA, 10% of the world energy is made out of nuclear energy, nuclear power plants. In Brazil, if you don't know, in Brazil we do have nuclear energy. We have the Angra power plants. We have Angra 1, Angra 2, and we should have Angra 3, but we do not. And mostly the energy used is only for Rio de Janeiro, but yeah, we do have those. So the first Brazilian power plant, Angra 1, we can see that it started early, 1985, and it had like 640 megawatts of power. But as time passed, we got way better at nuclear energy. The second power plant, that is Angra 2, we have 1,350 megawatts of power. And that was at 2009, not the biggest of a difference in years. And now we're building Angra 3, like it should have been built already since it started in 1984, but we still do not have it built due to many problems and political things. We estimate that 65% of the power plant is done, but as of right now, it's not usable. And it should have about 1,400 megawatts, but since the technology has gotten better, since it may be better. And as we see, we took much more than 7.5 years in basically building the Angra 3. And that was the average of the time for building a power plant in 2016. So we're taking a long time in that. Here are some photos, Angra 1, 2, and 3 respectively. And answering the last question, what are the future prospects of nuclear energy? Well, as I said earlier, nuclear energy can be produced through fusion or fusing atoms together, and that's what the sun does. That's how it produces energy. And that's what we basically are researching. We do not know how to safely use it, or actually we're not even kind of capable of using. As of right now in Germany, they discover a way to make a fusion reactor, but it's still in the testing phase, so we cannot really affirm if it's safe and really capable of producing energy like a generator would, for example. And yeah, that's basically it. We're researching fusion and other ways of using nuclear reactor. Basically, we only use for producing energy, and we only use with water, the coolant that makes the turbine spin. So we're researching how to use with other things like molten salt or metals, and we are researching how to use nuclear power plants to desalinize water and stuff like that. Like we have some examples here. Um, like turning seawater into drinkable water and to decarbonize the industrial plant. So that's basically it. And also we are researching to make generators smaller, like have a very strong generator, but not that big. Because generators, the stronger they are, the bigger they have to be. So with nuclear, they can be of smaller size. That's basically the research. Here are the sources I use. If anyone wants a little more research about the tool. And yeah, thank you for attending.